Imagine waking up to the idea that everything you've ever known, your universe, your reality, is actually a colossal hologram, a shimmering projection from a deeper, unseen dimension. This isn't science fiction. It's a bold theory that could rewrite everything we understand about existence itself. So why should you care? Because if our universe is a hologram, then the rules we live by might be illusions, and the fabric of reality could be far more mysterious and extraordinary than we ever imagined. Stay with me as we unravel the mind-bending concept of the holographic universe and explore how it challenges the very nature of reality. The foundations of the holographic principle. The core idea behind the holographic principle arises from the intriguing relationship between gravity, quantum mechanics, and the nature of information in the universe. It suggests that the description of a volume of space can be fully encoded on its boundary surface, much like a hologram. This idea is rooted in the realization that the maximum amount of information, implying the number of possible quantum states, contained within a region doesn't increase with the volume, but rather with the surface area enclosing that region. This shift in perspective challenges our traditional understanding of space-time as a three-dimensional tapestry and hints at a more fundamental two-dimensional underpinning. Essentially, the universe might not be a three-dimensional object in its true essence, but a projection of information stored on a lower-dimensional boundary. A concrete example behind this principle can be found in black hole physics. When matter collapses into a black hole, its entropy, which correlates with the amount of information it contains, is proportional to its event horizon's surface area, not its volume. This was a groundbreaking insight because it defied the conventional expectation that information scales with volume. The laws governing black holes and Hawking radiation lend weight to the argument that the fundamental degrees of freedom of a gravitational system are encoded on a boundary surface. This boundary acts as a sort of holographic screen, holding all the data about what's inside. Extending this idea to the entire universe implies our three-dimensional experience could be an emergent phenomena from surface information encoded on a cosmic boundary. The mathematical formulations backing the holographic principle often involve string theory and quantum field theory. In particular, the anti-de Sitter/conformal field theory, AD/CFT, correspondence provides a specific realization of this principle. In this framework, a gravitational system in a higher dimensional space, the bulk, is equivalent to a quantum field theory without gravity on the lower dimensional boundary. This duality offers a powerful tool to examine complex gravitational systems by translating them into more manageable quantum field theories. It demonstrates, at least in idealized models, that space-time geometry and gravitational dynamics can emerge from purely quantum informational descriptions on the boundary, reinforcing the radical notion that our universe might fundamentally be a hologram. This foundation opens profound questions about the nature of reality and the limits of human perception. If the universe's information content is fundamentally stored on a boundary, then what we perceive as a continuous, three-dimensional world could be a projection, a kind of cosmic hologram. It aligns with the idea that space itself emerges from entanglement and quantum information processing at a fundamental level. Such a perspective reshapes our understanding of the universe, blending ideas from quantum theory, cosmology, and information science. The holographic principle thus offers a window into potential unification, hinting that gravity and quantum mechanics, often seen as incompatible, might be different facets of the same informational fabric. Quantum mechanics and information encoding. Quantum mechanics introduces a radical perspective on how information exists and propagates within the universe. At its core, it suggests that particles are not definitive points, but rather probabilistic wave functions, complex entities that encode all possible states of a system. This encoding process is inherently non-local, meaning the information about a particle's state isn't confined to a specific point in space, but is spread out across its wave function. When it comes to the universe itself, this principle implies that the total information of all particles and fields can be thought of as a vast, interconnected network, where each piece influences and reflects the others instantaneously through entanglement. Entanglement, a phenomenon where particles become linked regardless of distance, is central to understanding how information could be stored or transmitted in a holographic universe. In some interpretations, entanglement links create a web of correlations that preserve the overall information content, even if parts of the universe are separated by enormous distances. This principle forms the backbone of the holographic idea. The universe might encode all its information on a two-dimensional surface, akin to a hologram, with the three-dimensional experience emerging from this encoded data. The fact that information appears to be conserved and non-local in quantum mechanics fits snugly with the holographic hypothesis that the universe's observable phenomena might be projections of a deeper, information-rich structure residing on a surface. Recent advances in understanding black hole entropy have offered compelling clues. Hawking radiation, the theoretical emission from black holes, appears to carry away encoded information about what fell into the black hole, challenging earlier notions that information could be lost forever. Instead, it hints that the information is somehow preserved on the black hole's event horizon, a two-dimensional boundary. This process suggests that the fundamental description of reality might be shiftable from a three-dimensional picture to a two-dimensional surface, where all the information is retained in a way that can, at least in principle, be decoded. In essence, what looks like a chaotic, three-dimensional universe might be a complex but holographically encoded projection of data stored on a distant, two-dimensional boundary. Practically, this perspective is reshaping theories about the fabric of space-time itself. Quantum field theories, combined with holographic principles, have enabled physicists to imagine gravity and other interactions arising from a web of quantum information encoded at boundaries. For example, in the ADS/CFT correspondence, a major breakthrough in string theory, gravity in a bulk space is dual to a quantum field theory living on the boundary. This duality vividly illustrates how information in our universe could be encoded on a lower-dimensional surface, with the complex, three-dimensional reality emerging from that simpler, more fundamental set of data. In this light, understanding quantum mechanics and how it encodes information is not just a matter of particle physics, but also a glimpse into how the universe as a whole might operate on a holographic level. Cosmological evidence and theoretical support. The holographic principle finds compelling backing in both cosmological observations and theoretical frameworks that stretch the imagination of modern physics. One of the most persuasive pieces of evidence comes from the study of black hole thermodynamics, particularly the work surrounding black hole entropy. It turns out that the amount of information about matter falling into a black hole isn't stored within the volume of the black hole itself, but is proportional to its surface area. This surprising correlation hints at the idea that all the information contained within a volume of space could be encoded on its boundary, aligning well with the holographic hypothesis. Expanding beyond black holes, the cosmic microwave background, CMB, offers subtle clues. Tiny fluctuations in temperature across the sky suggest the universe's initial conditions were finely tuned in ways that resonate with holographic models. These minute variations imply that the total information content of the universe might be less than what one would expect if space were a traditional, three-dimensional stage. Instead, the universe appears to encode its information on a cosmic horizon, as if its fundamental description is two-dimensional and holographic in nature. Such findings bolster the idea that the universe's fabric may be fundamentally different from our everyday perceptions of space. On the theoretical front, string theory and quantum gravity frameworks heavily lean into holographic ideas. The ADS/CFT correspondence, proposed by physicist Juan Meldacena, stands as one of the most influential underpinnings. It posits that a gravity theory in a five-dimensional anti-de Sitter space, ADS, can be fully described by a quantum field theory on its four-dimensional boundary. This duality provides a concrete mathematical example supporting the holographic principle, as it demonstrates how a bulk universe with gravity can be equivalent to a lower-dimensional, gravity-free universe. Although our actual universe isn't exactly ADS, the principle offers a profound insight. Gravity and space-time may emerge from a less complex, boundary-based description. Furthermore, research into cosmic horizons and dark energy suggests that the universe's large-scale structure fits within a holographic framework. Observations of accelerating expansion imply that information about the universe's total content and evolution could be reliant on surface phenomena rather than volume. Recent thought experiments explore how the entanglement entropy, an idea borrowed from quantum information theory, may serve as a bridge connecting quantum mechanics, gravity, and the holographic paradigm, reinforcing that the universe could be a hologram at its core. These multifaceted lines of evidence underscore a growing consensus among scientists that the universe's grand architecture might indeed be a projection of some deeper, two-dimensional reality. Implications for reality and future research. The holographic universe hypothesis, at its core, suggests that the entire cosmos could be encoded on a two-dimensional boundary, much like a hologram projects three-dimensional images. If this holds true, the nature of reality becomes less like a solid object and more akin to a complex projection of information. This perspective profoundly influences how scientists and philosophers interpret phenomena such as quantum entanglement, black holes, and even consciousness itself. Instead of viewing the universe as a collection of separate, independently existing entities, it might be comparable to a vast, interconnected information network where each part reflects the whole. This radically different understanding could lead to new experimental approaches, such as investigating the universe's boundary conditions or searching for holographic signatures in cosmic background radiation. The implications extend into how we understand the fabric of spacetime. If spacetime itself is a holographic projection, then the fundamental particles and forces we observe are merely the surface manifestations of deeper, underlying information. That could mean gravity, for example, isn't a fundamental force but an emergent phenomenon arising from quantum informational processes on a holographic boundary. For future research, this opens possibilities for unifying quantum mechanics and general relativity, something that has long eluded scientists. Experiments might focus on detecting subtle deviations in the behavior of particles at high energies or small scales, where holographic effects could become apparent. Advanced telescopes and particle accelerators could eventually uncover observational evidence supporting the holographic principle, making it more than just a theoretical curiosity. In the realm of cosmology, embracing a holographic model could radically alter our conception of the universe's origins and its ultimate fate. If the universe's information is stored on a boundary, then information loss, such as what occurs around black holes, might be understood differently. Theories suggest that what appears to be a destruction of information is actually a transfer to a lower dimensional boundary, maintaining the total amount of information in the universe. This challenges the notion of cosmic and physical determinism, prompting scientists to reconsider how information flows through spacetime. Looking ahead, this could influence future research on black hole thermodynamics, quantum gravity, and even the nature of time itself. Developing models that incorporate this boundary-based view might lead to breakthroughs in understanding the universe's birth, evolution, and potential end. Overall, exploring the universe as a hologram pushes current scientific boundaries and invites inquiries into the fundamental structure of reality. It encourages interdisciplinary efforts, combining quantum physics, information theory, cosmology, and philosophy. As technology advances, scientists may develop ways to test these ideas more directly, perhaps through quantum computing, sophisticated simulations, or brain-inspired models that mimic holographic principles. Such progress could transform our comprehension of existence, blurring lines between physical and informational realms, and opening new pathways for understanding the universe's deepest secrets. In the realm of the holographic universe theory, the idea that our three-dimensional reality is actually a projection of information encoded on a two-dimensional surface challenges traditional notions of physical existence. This concept is rooted in black hole physics, where scientists observe that the amount of information contained within a black hole correlates precisely with its surface area, not its volume. This groundbreaking insight implied that the universe's fundamental fabric might be akin to a hologram, a vast, multidimensional projection where all the data necessary to describe our universe is stored on a distant, boundary-like surface. One of the most compelling illustrations of this theory comes from the ADS/CFT correspondence, a principle within string theory that suggests a deep connection between gravity in a higher dimensional space and quantum field theories on a lower dimensional boundary. In simple terms, phenomena occurring within a volume of space could be fully described by information encoded on its boundary, much like a hologram contains a full image on its surface. This idea has profound implications. It hints that the universe's apparent thickness and depth might be illusions, with all the physical interactions, particles, and forces actually emerging from a more fundamental, two-dimensional information layer. Examples from quantum physics bolster this perspective. Entanglement, for instance, hints at a hidden interconnectedness of particles regardless of the distance separating them, an aspect that aligns with holographic principles suggesting that the entangled states of particles could originate from boundary data. Researchers have used these holographic models to better understand black holes, quantum gravity, and even the nature of space-time itself. Through these models, complex phenomena like the emergence of gravity from quantum field theories are seen as a natural consequence of the universe's holographic structure, where the intricacies of space-time unfold from underlying informational patterns. Practically, this framework influences ongoing research in the quest for a unified theory of physics. If our universe truly functions as a hologram, then resolving the puzzles of quantum gravity and understanding black hole entropy become interconnected challenges. It also opens doors to novel computational models, where the universe's behavior could be simulated as a complex information processing system. The holographic universe theory pushes scientists to rethink the fabric of reality, suggesting that what we experience as three-dimensional space may be a rich, emergent phenomenon rooted in a simpler, two-dimensional informational reality. So, that's the fascinating idea behind the holographic universe, how our entire reality might be a projection, a deeply intricate illusion encoded on a distant, two-dimensional surface. We've seen how this theory bridges the worlds of physics, consciousness, and the fabric of existence itself, challenging our assumptions about what's real and what's illusion. It's a mind-bending concept that invites us to see the universe not just as the world outside us, but as something interconnected and deeply mysterious. If this resonated with you, or sparked more questions, first encourage you to keep exploring these ideas. There's so much more to uncover about the nature of reality, and first look forward to sharing more insights and discoveries with you in upcoming videos. So, hit that subscribe button, stay curious, and let's keep diving into the wonders of the cosmos together. Thanks for watching, and see you soon. There's a universe of ideas waiting just beyond the horizon.